A gasket is a mechanical seal which fills the space between two or more mating surfaces, generally to prevent leakage from or into the joined objects while under compression. Gaskets allow less than perfect mating surfaces on machine parts where they can fill irregularities. Gaskets are commonly produced by cutting from sheet materials. Gaskets for specific applications, such as high-pressure steam systems, may contain asbestos. However, due to health hazards associated with asbestos exposure, non-asbestos gasket materials are used when practical. It is usually desirable that the gasket be made from a material that is to some degree yielding such that it is able to deform and tightly fills the space it is designed for, including any slight irregularities. A few gaskets require an application of sealant directly to the gasket surface to function properly. Some gaskets are made entirely of metal and rely on a seating surface to accomplish the seal. The metal's own spring characteristics are utilized. This is typical of some ring joints, or some other metal gasket systems such as those made by Greylock. These joints are known as ACOM and ECOM compressive type joints. Properties. Gaskets are normally made from a flat material, a sheet such as paper, rubber, silicone, metal, cork, felt, neoprene, nitrile rubber, fiberglass, polytetrafluoroethylene or a plastic polymer. One of the more desirable properties of an effective gasket in industrial applications for compressed fiber gasket material is the ability to withstand high compressive loads. Most industrial gasket applications involve bolts exerting compression well into the 14 bar range or higher. Generally speaking, there are several truisms that allow for best gasket performance. One of the more tried and tested is, the more compressive load exerted on the gasket, the longer it will last. There are several ways to measure a gasket material's ability to withstand compressive loading. The hot compression test is probably the most accepted of these tests. Most manufacturers of gasket materials will provide or publish the results of these tests. Gasket design. Gaskets come in many different designs based on industrial usage, budget, chemical contact and physical parameters. Sheet gaskets. The premise is simple in that a sheet of material has the gasket shape punched out of it. This leads to a very crude, fast and cheap gasket. In previous times the material was compressed asbestos, but in modern times a fibrous material such as high-temp graphite is used. These gaskets can fill many chemical requirements based on the inertness of the material used and fit many budgetary restraints. Common practice prevents these gaskets from being used in many industrial processes based on temperature and pressure concerns. Solid material gaskets. The idea behind solid material is to use metals which cannot be punched out of sheets but are still cheap to produce. These gaskets generally have a much higher level of quality control than sheet gaskets and generally can withstand much higher temperatures and pressures. The key downside is that a solid metal must be greatly compressed in order to become flush with the flange head and prevent leakage. The material choice is more difficult. Because metals are primarily used, process contamination and oxidation are risks. An additional downside is that the metal used must be softer than the flange in order to ensure that the flange does not warp and thereby prevent sealing with future gaskets. Even so, these gaskets have found a niche in industry. Spiral wound gaskets. Spiral wound gaskets comprise a mix of metallic and filler material. Generally, the gasket has a metal wound outwards in a circular spiral with the filler material wound in the same manner but starting from the opposing side. This results in alternating layers of filler and metal. The filler material in these gaskets acts as the sealing element, with the metal providing structural support. These gaskets have proven to be reliable in most applications, and allow lower clamping forces than solid gaskets, albeit with a higher cost. 2. Constant seating stress gaskets. The constant seating stress gasket consists of two components. A solid carrier ring of a suitable material, such as stainless steel, and two sealing elements of some compressible material installed within two opposing channels, one channel on either side of the carrier ring. The sealing elements are typically made from a material, vermiculite, etc. suitable to the process fluid and application. Constant seating stress gaskets derive their name from the fact that the carrier ring profile takes flange rotation into consideration. With all other conventional gaskets, as the flange fasteners are tightened, the flange deflects radially under load, resulting in the greatest gasket compression, and highest gasket stress, at the outer gasket edge. Since the carrier ring used in constant seating stress gaskets take this deflection into account when creating the carrier ring for a given flange size, pressure class, and material, the carrier ring profile can be adjusted to enable the gasket seating stress to be radially uniform across the entire sealing area. Further, because the sealing elements are fully confined by the flange faces in opposing channels on the carrier ring, any in-service compressive forces acting on the gasket are transmitted through the carrier ring and avoid any further compression of the sealing elements, thus maintaining a constant gasket seating stress while in service. Thus, the gasket is immune to common gasket failure modes that include creep relaxation, high system vibration, or system thermal cycles. The fundamental concept underlying the improved sealability for constant seating stress gaskets are that if the flange sealing surfaces are capable of attaining a seal, the sealing elements are compatible with the process fluid and application, and the sufficient gasket seating stress is achieved on installation necessary to effect a seal, then the possibility of a gasket leaking in service is greatly reduced or eliminated altogether. Double-jacketed gaskets. Double-jacketed gaskets are another combination of filler material and metallic materials. In this application, a tube with ends that resemble a C is made of the metal with an additional piece made to fit inside of the C, making the tube thickest at the meeting points. The filler is pumped between the shell and piece. When in use, the compressed gasket has a larger amount of metal at the two tips where contact is made, and these two places bear the burden of sealing the process. Since all that is needed is a shell and piece, these gaskets can be made from almost any material that can be made into a sheet, and a filler can then be inserted. This is an effective option for most applications. Cam profile gaskets. Cam profile gaskets are used in many older seals since they have both a flexible nature and reliable performance. Cam profiles work by having a solid corrugated core with a flexible covering layer. This arrangement allows for very high compression and an extremely tight seal along the ridges of the gasket. Since generally the graphite will fail instead of the metal core, cam profile can be repaired during later inactivity. Cam profile has a high capital cost for most applications, but this is countered by long life and increased reliability. Flange gasket. A flange gasket is a type of gasket made to fit between two sections of pipe that are flared to provide higher surface area. Flange gaskets come in a variety of sizes and are categorized by their inside diameter and their outside diameter. There are many standards in gasket for flanges of pipes. The gaskets for flanges can be divided in major four different categories: sheet gaskets, corrugated metal gaskets, ring gaskets, spiral wound gaskets. Sheet gaskets are simple. They are cut to size either with bolt holes or without holes for standard sizes with various thickness and materials suitable to media and temperature pressure of pipeline. Ring gaskets, also known as RTJ. They are mostly used in offshore oil and gas pipelines and are designed to work under extremely high pressure. They are solid rings of metal in different cross-sections like oval, round, octagonal, etc. Sometimes they come with hole and center for pressure. Spiral wound gaskets are also used in high-pressure pipelines and are made with stainless steel outer and inner rings and a center filled with spirally wound stainless steel tape wound together with graphite and PTFE, formed in V shape. Internal pressure acts upon the faces of the V, forcing the gasket to seal against the flange faces. Improvements. Many gaskets contain minor improvements to increase or infer acceptable operating conditions. A common improvement is an inner compression ring. A compression ring allows for higher flange compression while preventing gasket failure. The effects of a compression ring are minimal and generally are just used when the standard design experiences a high rate of failure. A common improvement is an outer guiding ring. A guiding ring allows for easier installation and serves as a minor compression inhibitor. In some alkylation uses, these can be modified on double-jacketed gaskets to show when the first seal has failed through an inner lining system coupled with alkylation paint. Reasons for failure: uneven distributed pressing force. Uneven pressing force is caused by a variety of factors. First is the human factor, asymmetric construction of the preload bolt. This factor can eliminate construction. Theory on the flange pressed: the sealing surface is absolutely parallel to the practice, however, the centerline of a pipeline cannot be absolutely concentric, and thus tighten the bolts on the flange moment, so that the flange discontinuity. Asymmetrical connection: the sealing surface more or less deformed, so that seal depressing force is reduced, the running load, prone to leakage. Third, the density of bolt arrangement on the pressure distribution: more obvious impact, the closer the bolts, the more uniform the pressure. Stress relaxation and torque loss: tighten bolts on the flange, due to the vibration of the bodies, the temperature increased or decreased and other factors, the working process of the spiral wound gaskets. Stress relaxation: the bolt tension will be gradually decreased, resulting in loss of torque, causing a leak. In general, long bolts, the remnants of the torque, the smaller the diameter the more advantageous to prevent the loss of torque, with long, thin bolt is an effective way to prevent torque loss. Heating a certain period of time to make it stretch the bolt, and then to maintain a given torque, is very effective to prevent the loss of torque. There is a gasket is thinner and smaller the loss of torque. In addition to prevent the strong vibration of the machine and the pipe itself, and exclude the impact of adjacent equipment vibration, the impact of the sealing surface is not meaningless. Not to beat the bolts tightened, can prevent the loss of torque. Surface not smooth: it is important to make the sealing finish proper, otherwise it will cause leakage. Temperature: flange leak often occurs in the cooling, because the cooling rate of cooling when the flange and bolts do not after cooling, the pressing force of the metal gasket's stress relaxation, combined with the cold contraction of the pipe, resulting in toward the bolt tensile direction force. This force will lead to leaks in, where the low temperature media. Occasions when gasket should be noted: 1. Low temperature flexible gasket. 2. Shim thickness should be as much as possible to take a small flange gap as small as possible. 3. High strength bolts, so that the strain is small. See also, O-ring, ozone cracking, polymer degradation, vacuum flange, washer. Sources: 1. Bickford, John H. An Introduction to the Design and Behavior of Bolted Joints, 3rd ed., Marcel Decker, 1995, pg. 5. Platt, Dr. Jorge and Rossi, Claudio, High-Temperature Behavior of Compressed Fiber Gasket Materials, and an Alternative Approach to the Prediction of Gasket Life, FSA Presented Paper, 1995, pg. 16. External links: Gasket Fabricators Association, Fluid Sealing Association, Gasket Division, Gasket Selection, http, European Sealing Com. About Divisions, Flange Gaskets Division, Gasket Materials Informative Resource, Expanded PTFE Joint Sealant User Guidance Informative Source, /Gasket Failure Reasons, Informative Source, Gasket Materials, Informative Source, PTFE Gaskets.